Il y en a d'autres quand je veux la changer. Ça va? Vous avez besoin de quelque chose? Et Ariel aussi. Et Xavier, comme il n'est pas là.
Mais c'est lui qui doit valider parce que j'ai mis la liste.
Ça va bien se passer. Salut, Janine, c'est.
Par contre, quand tu as des deux chaînes.
C'est pour ça que moi, je n'ai pas fait un jury pareil, tu sais. Il est passé loin. Non, c'est vrai que moi, j'en avais trois qui étaient en ligne. C'est moi. Ouais.
Après, tu stresses un peu plus pour aborder les fonctions.
Mais tu me délègues à tout, hein.
Moi, par exemple, le fait de l'avoir.
Ah oui, bah oui.
Ça doit avoir plus d'argent en jour.
Pour moi, dans le coup, ouais. Merci. Si tu veux, mets-toi là où tu vas, ça va aller. Parfois, j'aurais juste capté un regard. Voilà.
Oui, mais là.
Parce qu'on avait enlevé à un moment le truc pour aller il a enlevé ça pour mettre sur la journée.
Super. On voit le. Non, c'est bon. Bouteille d'eau, une bouteille d'eau.
Les avignons, s'il vous plaît. Je demande à moi. C'est pas rien. Ah, petit cafard, ça porte une. Regarde. Il est mort en plus. C'est. Tu veux qu'on se mette dans des endroits précis ou pas? Dans la salle?
Moi, je
Juste pour les
avec
franchement, ici, on n'est pas. Moi, je ne vais pas avec ma famille. Parce que comme j'étais comme lui, comme ça, je ne voyais pas.
moi, je n'ai pas besoin de voir ma famille. Moi, voir mon père, ça va me rajouter des stress.
Ok, donc ton père, je vais lui dire que c'est. Ça va, ça va. Je te laisse ma chérie là-bas. Voilà.
Non, mais merci d'être
Installer
Oui, oui,
je sais pas. Hein?
Je vais laisser la première rangée pour la famille.
Ok.
Ouais. On les deux, quoi. On va dire. Du coup, c'est toi qui le fais. Ça veut dire que c'est par la fin, du coup, que je vous ai envoyé tous les deux les liens. Ah, ça fait? Ouais.
Ça va, tu es prêt? Bien sûr, c'est absolument sûr que je vais faire les experts. Et tu comprends ce que Anne est coincée à.
Oui. C'est pas grave, hein, après.
Ouais.
Elle ne m'avait pas répondu, elle. Mais...
Ah ouais.
Pourquoi j'ai l'impression que c'est sombre? Ah, j'ai l'impression que c'est sombre.
Un petit peu, mais ça chauffe.
Non. Ouais, c'est en train de s'éclaircir.
Envoyer la montagne.
Comment tu me fais?
Pour le son, pour le faire de.
Elle est belle.
Ouais, c'est pratique. Minutes, ça va?
Oui, ça va.
Salut Olivier.
Bonjour.
Autorisable, quand la reine.
Ah, enchantée. C'est aussi.
Très bien, vous prenez, merci madame.
Je vous en prie. Pas de problème. Pas de problème.
Merci.
Voilà, tu pouvez venir. Voilà.
Vous vous rencontrez.
Ah oui. Vous entendez bien parler? Ah oui, d'accord. Tant bien.
Donc, ça c'est la main.
Bonjour. Entendez, entendez. Bonjour, bonjour.
Si Akram qui est bon, on peut dire, bien un peu de bonheur. Merci.
C'est madame. Vous faites partie de la maison. Vous faites partie de la maison.
J'espère qu'on fait cette émission.
Pas grave.
Le soleil. On s'en sait, on révolution.
Merci.
C'est ma maman.
Merci. Donc, il y a eu simplement dans les donc, le lien est là.
Bonjour, est-ce que vous m'entendez? On va faire quelques tests de son et audio.
Oui, c'est bon, c'est bon.
Très bien.
Ok, merci.
Tu as déjà discuté avec Olivier pour savoir si vous arrivez à comprendre.
Ben, il a mais en tout cas, on va
Olivier? Olivier, tu nous entends bien?
Alors, nous, on ne t'entend pas parce que ton micro est coupé, mais voilà.
D'accord, bonjour à tous. J'entends pas bien la salle, j'entends des murmures dans la salle ou des bruits, mais j'entends pas bien ce qui se dit dans la salle.
Ah,
Oui. Est-ce que vous m'entendez bien là, si je présente?
tu m'entends là?
Oui, 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 j'entends bien la présentation, mais j'entends pas bien les commentaires dans la salle, disons.
C'est derrière.
Ouais, d'accord.
Et là, quand on prend la parole un peu fort, c'est bon?
Faut que je fasse très attention à ce qui se dit.
Bonjour, ami.
Ouais, bon, on va faire des choses pour améliorer et on dira si c'est mieux. OK? Mais déjà, je vais là. Et sur quoi là? C'est la musique. Non, c'est ça.
Lors de la séance des questions,
Voilà. On a pas encore d'arriver à 14 heures, c'est moins 3. Le dernier membre du jeu. Voilà.
Let's begin. We are gathered here today to attend to the PhD defense of Akram REDJDAL for the title of Doctor in Biomedical Informatics from Sorbonne University. So I'm Sandra Bringuet. I'm a full professor at the University Paul Valéry in Montpellier, and I have the great pleasure of sharing your PhD defense. And I will take a moment to introduce the member of the jury. So I will start with two thesis referees. So Olivier Boden-Ryder is remote. He's senior investigator at Winston Hill National Center for Biomedical Communication. Silvana Caglini is full professor at the University of Pavia. Lina Swamia is a full professor at the University of Rouen. Marc Poudia is full professor at the hospital practitioner at the University of Rennes. And Jacques Beau is research scientist from HPHP. And Joseph Grigorov and Brigitte Serroussi are both full professor and hospital practitioner at Sorbonne University. So you have 40 minutes to present the key highlight of your contribution, and each member of the jury we have the opportunity to discuss with you. So let's start.
Thank you very much for this introduction. Hello, everyone, and thank you for coming to the defense of my thesis entitled Symbolic and Numeric Artificial Intelligence for Learning Complexity of Breast Cancer Cases and Providing Decision Support for Their Therapeutic Management. It was directed by Professor Brigitte Serroussi, co-directed by Professor Joseph Grigorov, and co-supervised by Dr. Chaglini. So the clinical context of the disease is the breast cancer, which is the most common cancer among women, with more than 2 million new cases worldwide in 2020, and its burden is continuing to increase as we predict 40% increase by 2040. In many countries worldwide, multidisciplinary tumor boards have been introduced to provide collaborative and multidisciplinary decision to breast cancer patients. During the MPBs, the clinicians group together to discuss all cancer cases, and they provide the decision for this clinical case. All this information is synthesized into a textual document that we call a breast cancer patient summary. So despite the fact that MTBs have been proven to improve the care quality by augmenting the compliance of the clinicians to the clinical practice guideline. However, the benefits are now being questioned because of the increase of breast cancer cases and the lack of time to efficiently discuss all the cases. On the other hand, there are clinical decision support systems that are computerized systems that are created to help healthcare professionals in their decision making. They are based on patient data and provide treatment recommendations or diagnosis depending on what we want to do with them. And most of these clinical decision support systems are based on the clinical practice guidelines. So we know in the literature that guideline-based clinical decision support systems have the capacity to improve decisions of the clinicians, compliance of the clinician's decision to the clinical practice guidelines. And we also know that the compliance with clinical practice guidelines has an impact on breast cancer survival rates. So we believe that implementing guideline-based decision support systems should have an impact on breast cancer survival rates. So to delve deeper into these systems, we did a scoping review where we took two keywords, breast cancer and decision support systems. We excluded all the papers that talked about image analysis or diagnosis. And from 200 initial papers, we arrived at 17 papers that talked about 15 clinical decision support systems. So there are two main categories of these decision support systems. There are risk calculators that may estimate the impact of the positive impact of a treatment on the survival rate. And there are therapeutic decision support systems that may be guideline-based or may be mixed with the data-based techniques. So we wanted, during this review, to see if the clinical decision support systems are used in clinical routine. And what we found is that most of them are rarely used. And if they are used, they are only used during small periods of time for the study. So in the LIMIX, we worked on the European project Désiré that aimed to create a multidisciplinary platform for breast cancer management with the three modalities of decision support, a case-based modality, an experience-based modality, and the guideline-based modality. In the LIMIX, we were responsible on the guideline-based part. So the guideline-based system is built on the 2016 APHP guideline. It enables the representation of patient data and clinical practice guidelines via an ontology of the domain that is called the breast cancer knowledge model. So during the evaluation, we found that there were some clinical cases where the recommendation of the system was not complying to the decision of the MTB. These patient profiles are not correctly covered by the clinical practice guideline. So we said that we should consider these patients as complex cases, and for these cases, the guideline-based decision support systems are not compliant, are not relevant. And when we asked the clinician what do they want as a decision support for them, they estimate that a recall of similar patients may be a good decision support. So to sum it up, there are MTBs, the effectiveness of MTBs is being challenged, mainly because of the increase of the number of patients and the lack of time to discuss all the patients. Guideline-based decision support systems, despite the fact that they may improve the clinician workflow, they are not used in clinical routine, mainly because they work only on patients covered by clinical practice guidelines, and it is also difficult to maintain them up to date. And finally, We have the notion of complex cases that are cases for which guideline-based decision support systems are not suitable. These cases need further discussion during the MTBs. And the problem is there is no clear definition of what is a complex case. So this raises many research questions. The first one is, how can we build a decision support system that effectively assists MTB clinicians in the decision-making process? What can be done to make clinicians use guideline-based decision support system, considering the complexity of cases, and how can we effectively update these systems? And finally, regarding the complex cases, how can we assist the clinicians in their management during the decision-making process? So our hypothesis can be resumed in a single sentence. One size does not fit all. Basically, we believe that a single decision support system is not efficient to treat all cancer cases. So we want here to create a system based on two modalities of decision support, a guideline-based decision support system for non-complex cases, and the case-based decision support system for complex cases. This suggests that we have to learn first how to detect if a cancer case is complex or not, before or prior to the MTB. And as we work on breast cancer patient summaries that are textual and unstructured documents, we need a structured data extraction part before starting to build this. So our thesis project got the approval of the ethical and the scientific committee, and we had access to the database from the PhD data warehouse with all the patients discussed during MTB at Turner Hospital between 2018 and 2022. So how I'm going to present this thesis? I'm going to start with the first part, which is the structured data extraction part. Then we move on to the complexity classification part. The third part is the update of the guideline-based decision support system of Desiree. So we won't create another guideline-based decision support system, we just reuse the one developed within the Desiree project. And finally, we finish by developing a case-based system for complex cases. So let's start with the first part. So for our goal here is to develop a structured data representation of breast cancer patient summaries. We started initially by using semantic annotators to extract structured data from the textual notes. And even though these annotators were good for a classification task, they were not satisfactory when extracting specific data related to cancer. For example, they lacked extracting the numerical values like the tumor size. They lacked extracting the stage, the DNA classification, all the attributes that we need. So we decided after that to use the entity attribute value model of the BCCAM ontology as a base to create a pipeline integrating rule-based techniques to extract structured data from this community. So why we are doing this? We are doing this to provide structured data for both decision support systems, the guideline-based and the case-based. So as I said, we work on textual breast cancer patient summaries. This is how they look like in the data warehouse. So we have text that is de-identified already. And as we can see here, a patient came and did a mammography, then an MRI, then a biopsy, and finally we got the proposition of treatment. So the development data set to build our algorithm was consisting of 50 breast cancer patient summaries. And it was done, these patient summaries were annotated by 2 experts during 6 annotation sessions. As another tool, we have the breast cancer knowledge model. So as I said, it's a common ontology with all the knowledge needed to represent all the specification of the breast cancer domain. It is based on the entity attribute value model with 3 main entities, the patient, the breast, and the lesion. Each entity has its attribute and each attribute has its value. So keeping the same model as Desiree project, we have 3 main entities. The patient entity with the many attributes such as the menopausal status or the age, the side entity with attributes like the TNM classification, the lesion entity with attributes like the histologic type or size. And in addition to these 3 main entities, we have 2 more entities. We also annotate the diagnosis procedures and the treatment procedures because we want to know what treatment does have a patient did and what diagnosis procedure we follow. So let's see the annotation process. So we have the initial breast cancer patient summary. We used the broad annotation tool to make an annotation scheme. So basically, we have all the attributes that I talked about in the precedent slide, and the experts can annotate data using this tool. We also annotate the contextual information. So we can see here that we can annotate the negativity, the family, the hypothetic attributes, and the negative attributes. So this is what an annotated breast cancer patient summary look like. And we also annotate the relations. So we have, for example, here the surgery that is related to the left side. We have all the attributes of tumors that are related to the tumor. So how our algorithm works, we start with the textual breast cancer patient summaries. We have regular expressions to match the name of the sections. So usually a normal breast cancer patient summary starts with a historical disease. Then here we have mammography, MRI, and then biopsy. So let's take, for example, this section biopsy. Once we extract the section, for each section we run our named entity recognition and contextual information algorithm. So basically we detect all the entities. So here, for example, we detected that the histologic type of the tumor is ductal carcinoma of grade 2 with positive hormonal receptor. Once we annotate all the entities and their context, we add the annotation of the relation. So, for example, here we can see that all the attributes of the tumor are related to the tumor, and that the tumor is located on the left side. And finally, at the end of the process, we get the data in the structured form. Just a small word about the name density recognition task. We use a package developed by the teams of the APHP named EDS-NLP, which enables the normalization of text and also has integrated pipeline to extract many entities. So, for example, we used the EDS pipelines for drugs, ICD-10 codes, and dates. We also use another system that is named Clarity NLP to extract the sizes and the PNM classifications because it was the best performing system for us. And for all the other attributes, specific regular expressions was implemented by me to detect the attributes. So for the evaluation of this part, we used 13 breast cancer patient summary that were pre-annotated by a preliminary version of the algorithm and then manually verified by an expert who did manual annotation of them. So basically what we noticed is that there are little attributes where the performance was poor. They are selected in red here, but what we notice is like when we have a few numbers of mentions of the attribute, then the algorithm struggles to detect them. And this is mainly due to the fact that we did not mention them a lot, so we did not find them a lot in the development data set, so we did not have enough rules to detect them. Just to focus on an example, he confirmed positive nodes. So this attribute is always expressed in a different way by clinician. So the rules we implemented were not sufficient to detect efficiently this attribute. Regarding the contextual information and the relation extraction, it was the same. We are good when it comes to attributes where it's mentioned a lot. We have a lot of negations, so we could implement a lot of rules that say, yeah, this attribute is negated or not. But for example, for the family, we did not have a lot of mentions, but we did not have a lot of rules to detect them. Again, regarding the relation extraction, we are good for all relation except the bilateral side. Bilateral breast cancer cases are rare, and we didn't find a lot of bilateral cases when developing the algorithm. So as a discussion, our rule-based pipeline showed overall good performance with an average precision of 81% and an average recall of 84%. It has competitive performance compared to similar tasks. So Ruby is a system developed by Nice Hospital that deals also with data for breast cancer. And we basically have same or better results than them in all attributes. We noticed poor performance in some attributes, so like the confirmed positive nodes, that suggest the need for future research and maybe implementing other NLP techniques to detect them. And finally, it's important to note that we evaluated only on a data set of 30 patient summaries, which is small size, even though there are many mentioned, but we still need more data to evaluate. So now we're done with the structured data extraction part. We can move on to the complexity learning part. So our goal here is to assess the complexity of a clinical case from the information provided in the breast cancer patient summary. Our approach is to use a supervised binary classification. We mainly compare two feature extraction techniques using semantic annotators that are rule-based and using the new pre-trained language models. Finally, once we get the features, we use several machine learning and also rule-based algorithms to detect the complexity. So why we are detecting the complexity? It's to do a algorithm that will serve as a triage system to know if you want to have a guideline-based decision support or a case-based decision support. So to do the work, we had access to semantic annotators. We use MetaMap as it's a widely used annotator for English language. Basically, it maps biomedical text to UMLS concepts. So we give it the text, and it gives us back the UMLS concepts in the text. And as we work on French summaries, we also use ECMD, that stands for Extracteur de Concept Multinomique. It's basically a French annotator that is based on bag of words algorithms and textual indexing. It doesn't provide the UMLS codes, but it provides codes in different ontologies and terminology. So for the annotation process during the year 2021, we asked clinicians of the MTB to annotate all the cancer cases as complex or non-complex. And we asked them to give us the reason on complexity. So if it was complex, why is it complex? This was the objective was to get a definition of complexity and to use rules to detect the problems. So here's how we execute the annotators. It's pretty simple. We prepare the BCPSs. As they have a lot of acronyms, we deal with the acronyms and the abbreviation in a proper pre-processing task. Then, as we work with MetaMap that is made for English, we translate the French patient summaries to the English. And once we have that, we run SAMT on the French summaries and MetaMap on the English summaries. We got the UMLS with the QEs and the labels in different ontologies, and we put them in the database. Once we had that, we started by implementing a rule-based classification. So basically, we took all the reasons of complexity annotated by the expert. We used SAMT and MetaMap to annotate these reasons, and we got a database of complexity-related concepts. And what we said is that if in a BCPS we have at least one complexity-related concept, then the case is complex. So it was a single concept threshold. So we published a work where we did actually what I just presented, and we compared it between several deep learning and machine learning algorithms. So for traditional machine learning, we use decision trees, random forest, and XGBoost. And for deep learning, we use MLB, CNN, and RNNs. So the best performing was MLB and XGBoost. That's why I'm going to present only MLB and XGBoost in this series. So the machine learning pipeline is quite simple. We have all the concepts, we put them, we do a k-fold cross-validation, we do a hyperparameter tuning, and then we assess using the precision method at F1. So the second method was to, instead of using semantic annotators, was to use the new pre-trained language systems. We used the transformer-based method. Actually, we used a BERT model that was trained on the PhD data warehouse. We know that BERT has a limitation of 512 tokens. So we did two strategies to deal with this limitation. First, the truncation strategy, where we kept only the 25 first tokens and the last 40 and the last approximately 480 tokens, because they contain the most up-to-date information. And the second strategy was the chunking strategy. So basically, we divide the BCPS into chunks of 512 tokens, and then we classify each chunk alone. And then the class that has majority takes the classification. We also try to use static word embeddings like word2vec and gloves. So basically here we don't have a constraint, we just use them to create the embeddings of the text, and then we do classification using the ML. So we worked on a total of 1,048 breast cancer patient summary that represent the patient treated between November 2020 and January 2022 at the hospital. We used 80% for training and 20% for test, and we used a five-fold cross-validation technique. All combination of the machine learning algorithm were submitted to grid search for parameters. So what we notice is that XGBoost and MLP are still the best performing methods. MLP is the best performing with the F1 score of 88%. And the rule-based method was the poorer one, detected a lot of false positives. And also what we may notice is that BER did struggle a lot finding complex cases. In fact, it classified all the BCPS as not complex. And when we look at the precision recall curve here, we can see that MLP is better than XGBoost in identifying the X classes. So, as a conclusion of this part, we noticed that models based on semantic annotators perform better than models based on pre-trained language model. The rule-based method did not work at all, but we believe it's because it was too simple. Only matching with one concept is too simple. And finally, MLP achieved the best performance with 88% effort score, which is quite good for us. And also the collaboration with the domain experts, so all the reasons of complexity that has been collected were used to provide a kind of definition of what is a complex case for the response. So now that we can detect the complex cases and that we have structured data, we can go on and proceed with the decision support systems part. So we start with the non-complex cases. So as I said in the introduction, we use for this part the guideline-based decision support system developed within the DESIRE project. And basically, the research question here is how do we update it? It is based on the 2016 guidelines, and how do we update the knowledge of the DESIRE, the knowledge base of the system. So our approach is to detect the changes in clinical practices using the decision support system of the DESIRE project. We compare the recommendation of the system with the decisions taken during the MTB, and if they are not complying, we go to the most recent guideline that is named SINORIF, and we check if the MTB decision is compliant or not. So this method was, the utility of this method is that it's an efficient semi-automatic method that enables to update the knowledge bases of guideline-based clinical decision support systems. So in this work, we use the structured data extraction algorithm we did in the first part. So we start with textual summaries. We use our algorithm, we get annotated summaries, and then an intern did a manual verification to put the patients in the system. So as a material, we have the guideline-based decision support system of the DESIRE project. We have the clinical practice guidelines, so the APHP of 2016 and SINORIF of 2021. And also we use 160 breast cancer patient summaries representing non-complex cases, because the system is for non-complex cases, and from all scenarios. So in DESIRE, we have the scenario concept. So we have 4 main scenarios. Scenario A, when it's an decision. Scenario B, when the decision is made after neoadjuvant treatment. Scenario C, when it's made after neoadjuvant treatment and surgery. And scenario D, when it's made only after surgery. So as I said, the first step is to extract structured data and put it into a representation in the BCKM ontology. So we did it using the structured data extraction algorithm. Then, once we have the recommendation of the system for a clinical case, we compare the recommendation to the decision made by the MTB. If the decision is compliant, then we suppose, and it's a strong assumption, that there is no evolution in the practice. If not, we check the recommendation for this case in the SENORIC 2021 guideline. And if it's not compliant to also the 2021 guideline, then we discuss the case with experts because it's not compliant with any guidelines. And if it was compliant, we move on and we check in which modality the non-compliance occurred with Desiree to try to identify the rules that were wrong and to modify them. So let's illustrate all this. Let's say we have a patient of 50 years old that comes after neoadjuvant chemotherapy and surgery, so scenario D, that has HER2 positive stages, and she had an incomplete response to the chemotherapy. So we transform the patient, we put it in the guideline-based decision support system, we get the recommendation based on APHP guidelines from 2016. And as we can see here, APHP says trastuzumab therapy, radiotherapy, and endocrine therapy, whereas the decision of the MTB for this case was to do a TDM1 therapy, a radiotherapy, and an endocrine therapy. So we notice here that the MTB decision is not compliant with the recommendation of the system based on 2016. So we have to go and check SENORIC. Once we check SENORIC for this case, we notice that the treatment proposed is TDM1 therapy, radiotherapy, and endocrine therapy, basically the same as the MTB. So we notice here that the decision of the MTB is compliant with the SENORIC. So there's a problem with our knowledge base of Desiree. We move on to the fourth step. So we take the initial rule in Desiree. So the initial rule says if we have an invasive breast cancer and we have a HER2 positive patient, and it is in scenario scenario C, then we do a trastuzumab therapy. So what we add here is the specification of the rule regarding the response to the chemotherapy. So if there's a complete response to the chemotherapy, then we pursue with trastuzumab, and if it's not complete, then we replace the trastuzumab with the TDM1 therapy. So as we can see here, we have the TDM1 concepts that was not present in the ontology. So the initial step before that was to add the concept in the ontology under the targeted therapy part. So as a result of this comparison, we had among the 160 cases that we used, only 39 were the recommendation of the decision support system was not compliant to the MTB. And among these 39 cases, only one of them was not compliant with the most recent guideline. And when we discussed again this case with an expert, he said that finally it was a complex case and it was wrongly classified as non-complex. So when we look at the modalities, most of the changes occurred for the surgery and the chemotherapy part. We had a total of 48 rules that were either modified, added, or deleted. So to conclude this part, it is important to note the updates of the clinical practice guidelines when they change. However, there is a lack of transparent indication of these changes. We searched in the literature if natural language processing methods were efficient to detect these changes, but we didn't find an efficient method. So we need of manual monitoring of new versions to keep the guideline-based decision support system up to date. We propose the method based on ground truth to detect medical practice evolutions. It was a cost-effective method that directly targeted all the patients' profile that came frequently and that had changes in the evolution in practices. However, it's important to note that when we read manually SENORIC, we also saw some practice changes that did not appear when looking at the clinical cases. So now that we're done with the guideline-based part, let's move on to the case-based part. So here, we want to create a decision support system for complex cases. Our goal is to leverage case-based reasoning to provide decision support tools for complex cases. And we have two main approaches. We compare using a single similarity measure to using multiple similarity measures according to the type of attributes, and we call this second technique the hybrid method. Once we implement the method, we use also optimization techniques to enhance the performance of each method. So as for the last part, here we use our structured data algorithm from part 1. We start from textual breast conservation summaries. We use our algorithm to get annotated data, and then it is manually verified. But this time, instead of putting it in the Desiree system, it was just summarized in a 2-dimensional table. So we started first by creating a gold standard. We used the complexity annotations to select a N1 corpus of 100 breast conservation summary containing 50% of complex and 50% of non-complex cases. This dataset was clustered by an expert into 18 clusters, and we got what we named the similarity learning gold folder. And we had also another dataset of 10 breast conservation summaries representing complex cases. And for each of these 10 patients, the expert calculated the 5 closest patients among the similarity learning dataset, so N1. And we named this algorithm, this dataset, the similarity evaluation dataset. So, as I said, we use 2 methods, a method based on a single similarity measure and an hybrid method. So for the single similarity measure, we take our table, we do some transformations. So we found in the literature multiple similarity measures. So for example, the cosine that is made for numerical attributes, the Euclidean 2, the Jacquard that is made for the categorical attribute. So what we did is we take each patient and we transform its variables so that it fits with the similarity measure. So for example, the Jacquard doesn't take size or numerical values as input. We change all the numerical attributes. So for example, we change the age to a binary. We said if the patient was old or not. And regarding cosine and Euclidean measures, we changed all the hierarchical variables that we had. So for example, the histologic type was transformed to binary, so either invasive or non-invasive cosine. But once we change, we use the similarity measure to calculate similarity between 2 patients, and we get the similarity matrix among all the patients. Regarding the second method, so we don't have to do transformations because basically it uses a similarity measure according to the variable. So we use Euclidean and cosine for ordinal and numerical variables. We use Jacquard for categorical variables, and we use the Wu and Palmer similarity measure for hierarchical variables. Once we have the similarity matrix, we also try to manually vary the weights of each attribute to get closer to the clusterings made by the experts. So once we calculate the measures, we wanted to optimize them. So for the single similarity measures, we used deep metric learning method. So our architecture was based on Siamese networks. Basically, Siamese networks are the neural networks used for similarity. And we use also triplet loss function. So basically, we have an anchor, we have a positive patient that is in the same cluster, we have a negative patient that is in another cluster, and the objective of the architecture is to minimize the distance between the anchor and the positive and to maximize the distance between the anchor and the negative. So to do the training, we Sorry again. So we use Siamese network. So our training initialization, we started with the N1 corpus of 100 BCPSs that were used for similarity learning. We take a small corpus of 18 cases representing one patient from each cluster. So we have 72 patients that rest. And then basically the pipeline is to iteratively add one patient from the rest of the database, add it into our database, we calculate the triplets, and then we do the neural networks to with the objective of minimizing the triplet loss. Regarding the hybrid method, we use classical optimization techniques. So basically, we fix three attributes with a fixed weight according to the experts to the expert choices. So triple negative, recurrence, and geriatric frailty are fixed. And then we use Optuna to propose weights for the other attributes between, and then each time we calculate weights, we calculate a new similarity matrix. We do clusters for this similarity, we create 18 clusters, and then we use the IRE, so the adjust rand index. It's a metric that is used to evaluate if two clusterings are the same. And basically, we calculate the adjustment index each time, and the objective is to maximize the adjustment index. Regarding the evaluation, so the N2 of 10 patients. For each patient, we add it to our similarity. We calculate the similarity matrix. Then we keep the most 5 similar patients, and we compare them to the most 5 similar patients annotated by the expert. So basically, the results are as follows. The best performing method was the hybrid method when searching the weight automatically. We noticed that the Siamese network method did not work at all. It kept the same performance as the Gaussian metric. And basically, even with no weights, the hybrid method performs better than the single similarity method. So as a conclusion for this part, we know that using weights, weight averages of different similarity measures achieve the best results. We explain that because it's based on the type, so it's logic to use a Jacquard similarity for categorical variables and the Euclidean for ordinal variables. And also the optimization technique allowed us to take into account experts' knowledge. We fixed the weight of the attributes where the experts said that it's important. The deep metric learning methods did not work good. We explain this by lack of annotated data. Only 100 BCPS is not sufficient to train a deep metric learning algorithm. And also, we still need an additional validation by domain experts. So we compared the results and we got an accuracy score, but we didn't show to the experts the 5 similar patients provided by the algorithm. So maybe these 5 similar patients are not from the dataset annotated by the experts, but maybe they are in fact similar. So we need additional evaluation. So to conclude, we started with the objective of developing a multi-faceted clinical decision support system for breast cancer management. Regarding the data, we started with data extraction part, where we built an efficient rule-based method for extracting data from breast cancer patient summaries. We could, with this method, identify attributes for which rule-based techniques do not work good, and they maybe need another technique. But it is still important to note that we lacked evaluation data for this part. Regarding the complexity classification part, we noticed that semantic annotators have a good performance for filter extraction, and also that traditional machine learning models are still efficient. Actually, they work better than the new models like BERT and Web. But however, we still need a deeper exploration of the transformer-based method, because now there are new models that are made for longer text, and maybe they will be more efficient. Regarding the update of the guideline-based decision support systems, we propose the grand root methodology based on real-world cases to identify the evolutions in practices. We efficiently identified profiles where the GLDSS knowledge base needed to be updated. But we did not do all the updates yet, so we have to do all the updates and evaluate the system again on non-complex cases. And finally, regarding the case-based decision support system, we evaluated 2 approaches, using a single similarity and using multiple measures according to the type. We noticed that using a measure specific to the type of variable is important, because it actually gave better results. However, here also we lack annotated data for the evaluation. We evaluated on 10, but it's important to know that it's huge work from the expert to compare each patient to 100 other breast cancer patient summaries. So yeah, it explains why we use only 10 breast cancer patient summaries. I think it's important to discuss some points. So yeah, we did a data extraction algorithm, and yeah, we put a lot of work to do it, but it is important to note that the quality of the text is really important. So yeah, in this BCPSs, we have sometimes a lot of errors. For example, we have a tumor of 17 millimeters that becomes a tumor of 17 meters. We have important and a lot of use of copy and paste from previous BCPSs. And also the identification algorithm of the data warehouse just put a lot of errors in the text. So I had to do a data cleaning step that was really important and really hard to do. The second important point to note is the limited time for expert involvement. So even though we could have annotations and we did the work, the evaluation data sets are small. We've been working with experts and trying to get their time during the 3 years of the thesis, and it's not always easy. So yeah, we surely lack evaluation data, but it's comprehensible because the expert does not have a lot of time for us. And finally, regarding the fact of using rule-based techniques and machine learning-based techniques, we noticed that we can't just decide that the machine learning will perform well or the rule-based will perform well. It varies according to the task we use. The guideline-based knowledge, even though if it's crucial when we're working on health data, it is quite hard to incorporate expert knowledge in the black boxes of neural networks and machine learning algorithms. So finally, with the perspectives, so yeah, the evaluation we only implemented and evaluated our algorithms on breast cancer patient summaries from Turner Hospital. So we are planning to do an internal and an external validation by using the algorithm to assess intersite and TB compliance. Basically, we want to take two centers from a PhD and compare automatically, as you have the algorithm, the decision, and see if they take the same decisions. We have to implement the system in routine practice to see actually if it helps the clinicians. The data warehouse is not used, it's only used for fitting data, it's not used for an interpret. So it's another part to do the system in clinical routine. Regarding case-based reasoning, so we want to implement the method on a larger database. We only use 160 patients. We want to see maybe with all the patients of 22 and 23 to see if really the method enables us to detect all the evolution on practices. Regarding the case-based reasoning, we need to explore further the deep metric learning techniques. And also, it's important to note that we only implemented the retrieval part. So we only retrieve similar patients. We did not yet implement the part where we visualize how they are and we use the decision we found. And finally, it's important to expand the system's scope beyond breast cancer. We only work on breast cancer here, but it's possible to do with other cancers. Thank you very much for your attention.
Thank you for your very clear, synthetic, and pedagogical presentation. We will now begin the question round, and we will start with Olivier Bodenreider with remote. Do you hear me?
Yes, thank you. Yeah, I would like to add my thanks to Akram for a very good presentation today. And so there's a lot in this dissertation. There's a lot of work. Akram's covered multiple techniques. The presentation of the written material and the oral presentation this afternoon is very logical, which helps somebody like me who's not intimately familiar with breast cancer treatment follow along and understand how the different pieces fit together, which is really important in this work because there's a lot of different elements that have been touched. I also noted that there's already practical implications of this work. For example, the update of the Desiree knowledge base that was direct contribution of this work. So there's a lot that's been done here. So moving into a more general thought here, I'm wondering whether the same work in 5 years is gonna show the same results. And I know I'm not gonna ask you to answer this question, it's a rhetorical question, but more specifically, I'm wondering whether the role of rule-based systems in the future is going to be the same as what it is today, given the availability of large clinical data warehouses. So I know that part of your work is based on a clinical data warehouse, but with the generalization and the increase in size of these clinical data warehouses, I'm wondering whether more work can be done directly, more knowledge can be extracted directly from the clinical data warehouses. And there's one anecdote that I would like to bring here in support of this. So I don't know if you guys know John Halamka. He is a bit of a celebrity in the US in the world of CMIOs, which is the clinical medical information officers in hospitals. He was at Harvard, and he documents part of his life, not just the technical issues, but the part of his life in his blog. And about 10 years ago, his wife got breast cancer. And so she underwent chemo, and I don't remember the exact details, but one particular issue is that she was administered paclitaxel, Taxol, and she had side effects of it, and in the form of numbness in her hands. And she was an artist, and of course, that was really detrimental for her painting and such. And so I'm telling you the story because at the same time, it was the development of I2B2 in Zach Kohani's shop in Harvard. And Jamhalenka went to them and essentially asked the question, whether, limiting the dose of Taxol or the number of Taxol chemos would actually be detrimental to his wife's treatment. And by interrogating the clinical data warehouse, they were able to determine that, well, there wasn't a clear benefit in going for a longer course of Taxol, and they decided together with the clinical team to go with a shorter course of Taxol. So that's, I think, is an illustration. Of course, it's one data point among a lot of breast cancer cases, but I think that's a significant anecdote in terms of the use of clinical data warehouses to support clinical decision. Another one is the work done by Nigam Shah at Stanford. And Nigam has created what they call the green button, which is essentially a way of recalling similar cases from the Stanford clinical data warehouse to support clinical decision. It's not just for breast cancer, it's for everything. And in addition to that, Nigam's team has created a consult not for patients, but a consult for doctors at Stanford who can come with a case and essentially look at the clinical data warehouse for similar cases with specific questions regarding diagnosis or treatment of these cases. So I think we'll see more of this in the future, and I would like to, to hear your thoughts about that. So how do we do this? Do I go with other questions, and or do we have Akram?
Maybe you can have interactive discussion. You can answer and you can. Okay.
That's good. So
thank you for bringing up this point. I don't believe that in 5 years from now we will stop using rule-based methods. Well, I think the database methods may improve actually the rule-based methods, and that's actually kind of what we're doing. So we have guidelines. Following them has a positive impact on the treatment, on the survival rate. So why would we stop following them? Instead of that, maybe using the data techniques to, for example, detect before which cases are good or are covered by the guidelines. Also, as you said, maybe using the data to find new things to add them into the guidelines. But I don't think I'm kind of supporter of rule-based methods, so I don't think in 5 years from now we'll be stopping them, but maybe improving them with the database methods.
Okay, thank you. I think another point that I didn't make is that Stanford normalizes all their data to the OMUP common data model, which also helps a lot when it comes to finding, similar patients and things, because by and large, you don't have to do as much data extraction as you had to do in your particular case? Yeah, go ahead.
Yes, thank you. So yeah, actually in our house we have I think it's the E2P2, but it's being implemented. OMOP is being implemented in the PhD data warehouse, but we did not get the accesses to the to an OMOP database. However, for the similarity, I tried to use the structured data from the data warehouse to calculate them. So basically, in the PhD data warehouse, what we have is ICD-10 codes, what we call CCRM in France. It's the codes for the acts done for the patient. And I used these codes and used the ICD-10 and to calculate similarity. So I had the codes for a patient and the codes for another patient, and based on the codes, I wanted to assess if they are similar or not. But I had poor results because basically what we code is that all patients have breast cancer, and if those who did surgery, they have the code of surgery, but it's not into the detail of what type of what is the histological type of the tumor, is it a size closer or not, and the other attributes. So that's why we actually decided to take the breast cancer patient summaries, because they actually have all the data that we need and the specific data of the cancer that actually in the data warehouse we don't find in the structured data.
No, I think you're right. There's a level of granularity that's not sufficient when clinical cases are documented with ICD, and hopefully with the advent of deployment of SNOMED CT and things that are more adapted to clinical description, results will be better in the future.
Yes,
So following up on the patient similarity cases, I was kind of surprised that you didn't try, to my knowledge, you didn't try to reuse existing patient similarity algorithms. So there's a lot of research that's been done there, probably not in the domain of breast cancer, but there's a lot of effort that's been done to compare patients. And I was wondering why you didn't further explore existing work there.
So we actually tried that. We explored the patient similarity networks work. It's named NetDX. I don't really remember who are the authors. So yeah, they provided a system based on R to do the calculations. But our problem was we had to map our data to how they want them to calculate the similarity, and it added the task of mapping our structured data to the structured data that NetDX takes as input. So yeah, we didn't deeply search, but it's a great idea. We will do it.
Okay, so I think I will stop there, and thank you again for your presentation. I hope there will be journal articles coming out of your work, because you've done important work that's been published in in conferences up until now, and I hope you have the opportunity to write a few journal articles so that there's more dissemination of your good work. Thank you.
That's the objective of the upcoming months, actually.
So thank you. We will now listen to Silvana Caglini.
Thank you for your presentation, Akram. And I'm also a supporter of the systems, guidelines, but to tell the truth, I'm now worried about how guidelines are generated by the scientific societies, how they are maintained. As I wrote in the report, you have managed in your thesis 2 different guidelines. One for 10 years ago, more or less 8, and yes, 2016, and the other one more recent. But they are 2 different guidelines. So I imagine that they are generated by 2 different society or organization. Or my dream is that our government will set up an organization able to put a stamp on an official guideline, but only one for, of course, one for each pathology. So if there would be one official clinical practice guideline for breast cancer, then we can also think to generate in parallel the textual version and the computerized version, at least the formalized version. And in that way, it would be very, very easy, much easy to maintain and update the guidelines according to the clinical evidence. No? So this is just a comment. I would like to know also your opinion, if you have a guess at the moment.
Well, I guess we have the same dream. Yeah, it's complicated. I mean, there's not even a national guideline. Each center works alone. Actually, just regarding your first point, these are different guidelines, but some of the people were the same. More of the group was participating in the writing of both guidelines. Yeah, I think we have to work on this, and we have to have at least a national guideline, because it would be much easier to update one guideline each time the knowledge evolves than having a guideline and another guideline. And despite the fact that it was written by some same people, the format of the guideline is really different. APHP is like 30 pages, Synovic is like 150 pages. So yeah, I don't know why the hospital institute are still not coming up with just a single guideline and having its textual part and its computerized part. It would be really easier to update them and to use guideline based.
There have been some national, local initiatives. For example, in Italy, we have some years ago that national guideline repository, but it failed after 2 years. Also in the US, there was the ADH organization, but yeah, it's okay. This was just a comment. Now I come to my first question. When Brigitte invited me to review your thesis, I accepted immediately because you faced a problem that I'm also facing in my project. That is the multidisciplinary treatment of cancer patients. Working for years in this project, we realized how difficult it is to implement in the practice this multidisciplinary treatment. Because in fact, at least in Italy, oncologists belong to the oncology department, psychologists belong to psychology department, nutritionists another department again, and so on. So putting them together is very difficult, but from our point of view, this also is reflected in different data repositories. So we do not have inside the hospital a unique repository with data about psychologists, data about oncology, and so on. So my question is, since it is not very explicit in the thesis, when you talk about patient data, do you talk about all these kinds of data or only the data related to the breast cancer?
No, we only use the data related to the breast cancer, and more specifically, we only use the breast cancer patient summary. And it's also maybe one of the reasons, because in the data warehouse, so we have a patient and then we have all the textual documents for the patient, and we have the pathology result, the radiology result, etc. But with the identification stuff, it's hard to come up with the last radiology result and the last pathology result. So that's why we took the breast cancer patient summary is the input. So basically, so I've been going to a multidisciplinary tumor box for a year, and what they have on the screen is like the file. They have the PDF file of the patient, and they discuss it. So this summary, it has all the information we need. So yeah, we had to do a structured data extraction part because it's only expressed in textual and natural language, but it contains all the information we needed, but only regarding the stuff.
Because, for example, I imagine that during the so-called shared decision making, it's very important also to know about the psychology of the patient, know what they think, what are their preferences, their values. So my second question was, if you manage during your work different natural language reports, the one written by the oncologist and the one written by the psychologist, they are very different in the way they are written. For example, in the oncologist one, you can find some numbers, it's easier in my mind to make some entity extraction. While processing a text written by a psychologist may be more difficult, but we have some experience in managing different texts.
Well, yeah, the closest I have to that is that, I mean, when there's a psychological issue or a psychiatric issue with the patient, it is expressed in the MTV. But yeah, it's really expressed in a different way. I mean, some attributes we wanted to detect, we failed into detecting them.
So probably it is already in some way structured.
It kind of summarized, but not
Summarized,
structured.
yes.
Yeah, kind of
It is
summarized.
Yes.
Yeah, so I don't remember seeing a lot of cases with psychological issues, but I know that we may, like patients with dementia and some psychological issues, complex cases. But it's basically it's written in the breast cancer patient summary, and but I agree with you that it will be much harder to extract entities talking about psychology stuff than to extract like sizes or histological types.
So is your ontology also dealing with this extra disease aspect? For example,
maybe
nutrition is very important in cancer patient, no? Because I was very surprised to know that 30% of patients died for malnutrition.
Well, it's worldwide.
It's a lot.
It's really a lot, yes.
Yeah.
Yeah, regarding the psychological, we don't have really a lot of entities regarding psychological stuff, but we have, we know that patients with dementia, patients with psychiatric problems are complex cases, and we search for mesh terms that represent diseases like dementia, psychological issues, and we use semantic annotators to annotate the text, and when we find the concepts of these diseases, then we just put the case as complex, and we calculate the similarity.
Okay. And now a different question. Another argument, you talk about the difficulty of putting together enough patients, to work. Now you know that there is a big emphasis on this synthetic data generation. So do you think that this technique could be useful also for your work?
I guess so. It's quite hard. We're working on patient data. You can't just use a large language model directly, but we can train one in the data warehouse. We didn't do this. I guess they have potential, and we want to explore this. For example, maybe comparing two texts or guidelines, or maybe photo for the entities. We didn't try them yet. We may try them, but it's important to keep in mind that we're working on healthcare data, and using generative AI with healthcare may be risky. So yeah, we try them, and we don't know it.
Okay. If I have time for one minute, yes. Sorry. completely changing the argument. Is your system already implemented and used? And if yes, which are the regulatory issues that you had to face? Because, of course, we have this very nice experience with our last applications, and since they are not commercial, I don't know, is it a commercial system? Since they are not commercial systems, so with the CE mark, you have to make a notification to the boards. In our case, is the Ministry of Health. I don't know in France it is the same, and it takes a long time before the approval and so on. So did you go through this process also before implementing it?
The hard part was to get the access in the data warehouse. We implement the system only in the data warehouse. So the system won't work if you want to execute it in an MTB, in clinical routine in live, because it's two separate things. The data warehouse is going to manage the data and explore the data, and there's another hospital information system, and we did not do at all the part of the hospital information system. It's actually one of the perspectives, but I guess it's really hard to get the approval with that. But yeah, we installed everything in the data warehouse, and it was really, really hard. So mainly installing the guideline-based decision support system of Desiree. It was based on, it's technical stuff, but it was based on Java. And basically in data warehouse, we only do data, so we have only Python and R and stuff to do data. So it was really challenging to install everything and to run it. A lot of technical work, maybe not useful to present, but yeah, it was really hard. Just because, versions of systems and to install everything. But yeah, actually now in the data warehouse, everything is working. The data extraction part, the complexity classification part, and both guideline-based and case-based.
Yeah, but my question was, is the system actually present recommendations to doctors?
Not to doctors.
Not to doctors. That's why, okay. That's why it's not at the moment. It's not a medical device. So
it's not yet a medical device.
It's not yet a medical. Okay, I understand. Yeah. Thank you. Thank you.
Thank you very much.
Thank you. We will now listen to Lina Swamia.
Thank you, Sandra. So I will first start with congratulate you about your manuscript, because it was I really enjoyed reading it. So I didn't read it as a reviewer did, but it was clearly written. But I think you have answered several questions that have been or comments of your viewers that in your enhanced manuscript you have included, but some illustrations are still missing. But in your presentation, that it was a smart presentation, in fact, with all the details and nice illustration. So the hypotheses have been clearly argued with why this task, why this project, why this thesis, and the research questions also have been nicely presented. So I have several questions. Maybe when I read your thesis, I said, right, there are 4 objectives. What is the link between them and so on? But here in your presentation, you have clearly showed why you are doing this and this and this in your pipeline, in fact. So the first question is related to the first part regards of the structured data extraction. I was really surprised, in fact, that you have used the same thing, and I think it's an old version you have used, because yes, the same thing, yes, but there have been several improvements, in fact, and it relies on 100 terminologies, and you can even extract UML3I and so on, and you don't need even one step. You have to translate from French to English some keywords and so on. So yes, but I was really surprised that you use this old version, but maybe yes, it's when you have implemented maybe a web service you have implemented to ask.
So I actually
On
will ask Stéphane Darmoni to give us the available version because we installed it in the data warehouse.
Okay. Okay.
And,
Yes, I think you can improve the result. Because
they actually said that there was a new version coming with the negativity because
Yes.
the ones we got didn't even have the negativity.
because we had a thesis in 2020 and 2019, and it was really to improve efficiency and not so. But it's just a comment. Okay, so the on regards this part, you have manually designed regular expressions.
Yes.
So maybe you can give us a kind of metrics about these regular expressions. And you clearly explained that without those rules, in fact, you cannot detect precisely all the entities and so on. So what would be another strategy, in fact, without those regular expressions, because you need manual.
I think the other strategy is using new machine learning and deep learning techniques, but these techniques need more annotated data. So it was either I do the work and I do a lot of rules, and so how I did the regular expression. So for example, let's say I'm looking for the estrogen receptor. I would search estrogen word in all the DCPS, all the data I have, and then I will check one by one the files, and I will build the regular expression that matches the maximum.
So my question is also how time
it took a lot.
Yes.
It took a lot of time, several months. No, I'd say 4 months to build all the rules.
Okay.
So yeah.
Sure.
So if we wanted to do something else, we would have needed more data annotated, and that's harder to do than manually implementing rules.
And one of the questions you have compared with Ruby, I don't know.
Yes.
How did you evaluate this? How did you do this comparison in fact with Ruby? I am missing some details about.
Actually, they have a paper, and in the paper they have attributes they extract, and these are the same attributes as us because they work on breast cancer.
Okay.
So histologic type, hormonal receptors, and basically they have almost the same number of mentions in annotation, so it's really comparable. And we just saw the performance. Compared the performance.
So you have installed Ruby on your
No. We just compared to the results written in the paper. We didn't use. Actually, it's planned.
On the same.
It would be good to have either the Ruby system and try it on our side, or give us our system.
Okay, thank you. Yes, and in the second part, you did complexity learning. Okay, so in one moment, in one of your slides, you did annotations with mesh. That's it.
Yes.
So
we did annotations using actually MetaMask.
But my question is related to there is a terminology of oncology. Simple. You didn't choose it, or
we filter actually the concepts we get from the same day. We filter on mesh term related to cancer and other labels.
I think it is biased because if it doesn't work well, so everything will be okay. Yes, and the question is related also to the French translation part. Why you did this translation part? Because each concept has similar concept in another language.
But when we give, because we use MetaMask also, it's made for English. And when we give French text to MetaMask, he really struggles detecting concepts.
But how you did the translation?
We used an open model, obvious NP model.
To translate your concepts into?
No, I translated the text.
All the text.
Into English, and then I run MetaMask on the English text, and I run the CMD on.
So can you maybe evaluate the impact of this translation on the results or not, if you have been used something else instead of translating, first annotating and then using the translation of the annotation and then
That's it.
in,
Cool.
in another
We
way.
didn't proceed like this.
Okay.
So it's it's a good idea. In fact, we published a paper where we saw that when we translate the text and we do English annotators plus French annotators, we get the most concepts we're looking for. So we did a manual review on just small number of CPSs, and we checked if they identified the concepts we look for. And we saw that using ACNT alone performs less than using ACNT plus MetaMap, and using MetaMap alone performs less than using both. So that's why we use both.
Okay. And in fact, in this complexity learning task, you have only two classes, in fact.
Yeah, complex and complex.
So is it that relate to the guidelines and or not? Is it complex and not complex, and that's it? You know, you don't have something in between.
No, when we did the task, we did not.
Okay.
But we may actually.
Okay.
Because when they classified as complex, it's not each time a new reason. So there are reasons that come up and return. So maybe it will be a multi-class classification, but say this one is cancer plus pregnancy, so it's difficult.
Okay.
This one is
If I have the third part is related to guideline based on non-complex cases. So maybe it was not the objective of your thesis, but I would like to have some details about the ontology you have used, how it have been designed, the number of maybe you don't have all these details, but the number of concepts and so on. And after that, you combine the ontology with rules. But my question is related is why you don't use semantic web pool language to formalize those rules and instantiating, in fact, your ontology with your cases in order maybe to have something.
Basically use the ontology to annotate directly the patient summaries. Is that your question?
Yes, it's not there, but my question is why your rules are not formalized using semantic web pool language, for example, which is.
Yeah, they didn't think of it. I mean, chronologically, it was, we learned the complexity, we need structured data, so we will use annotators. We don't need annotation of expert at all. We worked well with the complexity, and then we went to the guideline DSS, and we found ourselves without structured data. So we said, yeah, we need to extract structured data. How can we do it? Yeah, I build rules, and that's what I decided.
Just maybe a few comments on the ontology.
Yes, so
if you remember, it's not the scope
classes,
of your work, but
Jack knows more than me the number of classes, but it was basically done during the European project. So there was partners from other countries, and it really contained all the knowledge. It's based on the NCI thesaurus. So for each concept in the ontology, we have the equivalent of the NCI thesaurus. And yeah, we have three main entities, attributes that describe the entities. And then for the attribute values, we have either it's Boolean, numeric, etc., or it can be concepts in the ontology. So for example, the histologic type attribute, it will have concepts in the ontology as types. For example, invasive ductal breast carcinoma, in situ carcinoma.
Maybe last question on that. So you know that you can use, in fact, knowledge graphs to represent the sizing of data and knowledge and rules. So do you think it is adapted to your case here? And if yes, how would you do?
We actually want to explore this knowledge graph step in the case-based reasoning task, because we are doing a lot of, we did manual work to just put the data in 2 dimensions. We choose this because, it was the last part, so less time for it. So we choose the simpler representation. But yeah, we are definitely going to work on the knowledge graphs. But I don't know, maybe I'm wrong, but I guess these methods need more data to work well.
Yes, in fact, it works when you have larger.
And we go back to the problem of getting the
Sure. And I liked also your conclusion and the perspectives because you showed clearly where you have to work additionally with to improve, in fact, your process. But maybe a general question. So you have, as a researcher, you have done this work. So how do you position this research on regards of what is done in the state of the art?
Yeah.
And how you can, because also this is related to breast cancer. Do you think it could be something generalized or not? Or it's too specific to those guidelines in French and those.
So
It's a.
yeah,
Okay.
I just go back to this slide to give you an idea of what are the decision support systems that actually exist for the management of breast cancer. So we have these ones here. So here they was developed by our team. So this system were used in clinical routine on Oncodoc, but it was stopped after 3 years.
Okay.
The main reason was the fact you have to manually answer to the questions of the system to get the recommendation. ABM Watson, that they were selling a huge system, and now they are not using it because it did a lot of wrong things. So basically, most systems are not used. Why? Because we have to reintegrate data, because guideline-based decision support systems do not work on complex cases, and we have a manual steps to do. And actually, the idea of our thesis is to avoid all these manual steps by taking the input, the same input as the MTB, because the MTB clinicians take the breast cancer summary as the input and give them as output recommendation without having the need to manually do anything. Actually, if we are able to implement it in routine, the idea is that the clinicians do not have to do anything. They will just have the cases. It says if it's complex or not, and it gives the recommendation at the end.
Okay. Okay, so thank you so much for your answers. Thank you so much.
Thank
It's
you.
your turn now.
Yeah, thank you. It's a privilege to be at the very end of the members to ask the question. So there are a lot of questions I would like to ask, but you broke the answer before. So firstly, I really appreciate your work. Your presentation was very clear and pedagogical, and we see all the system, how it could work and works in real life. So congratulations to all this work. And just one first question: what was the part you do yourself in the several in each of the part of your cases? I mean, did you rely on the help from the PhD data team, or to develop the pipeline of data extraction?
Except the experts annotation, for the data extraction pipeline, I did basically everything. For the complexity learning, I was doing everything too. And for the last two parts, I was supervising master students that worked, and after they finished, I continued working on it.
Okay, so you supervised master students yourself?
No, I co-supervised.
You could supervise, but you were in a position to co-supervise.
Yeah.
That's a good point. So I had some question about the data quality, because you focused on the NTB reports, and we had an experience in my university. We carried out many years ago a project called the Aztec, and the use case was not the same. It was to try to include patients into clinical trials, and we compare eligibility criteria to the clinical data, and try to find out if the patient could match to the trials. And yeah, we had 10 years ago the same conclusion that in the MDT reports, there are very specific things about cancer, but just minimal things, and a lot of information come with the physician during the meeting. And it's displayed in the screen. The report is displayed on the screen, but discussion and a lot of information that influence the decision is brought by the by the members of the teams. And so you attend to MDT, and do you have the same conclusion about the quality of the quantity of the information that within the reports and the difference with what is discussed during the meeting?
Well, when I was attending, I actually, maybe I'm wrong, but I actually thought they was, presenting all the things. I rarely saw them presenting something that was not written somewhere. However, there was some times where they went to check other documents from the EHR, and yeah, it was rare, but it happened. But the thing is that with our pipeline, we can extract data and we can put them into the decision support. And the decision support, when it doesn't have enough data to produce the recommendation, it says which data is missing.
Okay.
So yeah, our pipeline maybe enables also the fact to detect what are missing data in the breast cancer summary. But the quality I've been talking about is errors, because errors are you can't tell the system to detect that tumor is in the left if it's written that it's in the right, and in fact it's in the left, and it happens a lot in summary.
So okay, thanks. In your manuscript, you said you wrote that you could improve your pipelines of information extraction by using deep learning approach, especially because sometimes you have abbreviations or things that are not so regular. So why did you you didn't go more in this direction? It was because the time, or
So, yeah, the short answer is like lack of annotated data.
Okay.
But what we did actually is, we have to do the rule-based algorithm. We use 80 breast cancer patient summary. I started actually to use these 80 breast cancer patient summary to implement machine learning and deep learning algorithms. But now I only focus on attributes where the rule-based was not performing well. Because for the other attributes, for the legend entity, all the attributes are, except one attribute, all the attributes are about 95% of accuracy and on. So yeah, we could identify attributes where we don't have to, implement machine learning algorithms, so be more ecological, more computer friendly, and use only rules. But yeah, I started working on extracting the other attributes with machine learning techniques that was developed by people in the lab actually.
Okay, it's clear. I have one question. I have a question about your choice to have your own information model. You choose EDA structure data, and I knew that there is some initiative to try to standardize the information model for decision support systems. So the idea is, for example, I remember there's an initiative called Virtual Medical Reports from HL7. Really, that's changed from this. There are a lot of changes from this initiative and improvements. But why did you didn't choose to use a standard representation? Because if you want to push your system in the industry, for example, if there are some standard initiative to have data in the interoperable for decision support, you could leverage this kind of models.
Yes, so yeah, I didn't explain it, but I got a backup slide. In fact, the DZA component has, when we create a patient in DZA, it moves by a FHIR patient.
Okay.
So we have a FHIR representation of the patient when we use the GLDSS. It's actually here. It's written here. Here.
Okay.
So we have a FHIR by a parser in the system.
Okay.
So yeah.
Okay.
When we create the patient in the system, we have a interoperable.
It's not a matter of science, but it's a matter of engineering, and it's the idea is that your system could be plugged to a hospital information system. So you have to think about that.
Yeah. But I don't know actually what interoperable model they use in the RPHP.
At the bedside, it's FHIR.
Okay.
At the bedside, it's FHIR.
So,
So if you one day you want to implement your system, it has to be included in the FHIR APA.
yeah.
I mean,
So it actually is.
okay. No, just to thanks for your fantastic work. I think that I really like your approach to separate complex and simple cases, and for complex cases, actually it's up to the clinician to decide, and for the simple, it's up to the automatic approach to perform. So I like this approach. Thank you very much.
I would just say, we're not building a system that decides in the place of the doctor.
Yeah, for sure.
And for the complex cases, to help them, we would propose the similar patients, and we would say, these are similar patients. This was done for them, and you decide.
Okay. Thank you.
Thank you very much.
Thank you. So it's now my turn to ask my questions. So first, I would like to say that I appreciate a lot your manuscript and your presentation today, which allow both a very substantial quantity of work at the intersection of a very active research area, medical information and intelligence artificial. So many questions have already been asked, but I have some. No, first I will focus on your chapter dealing with complexity learning. So it was not so clear for me that you have no clear definition of complexity. You answer that it's possible to make a multi-class classification based on the causes, but of course, is there a notion also of temporality? Because I imagine that a patient can be a non-complex case and become with the time complex. Could you tell me how you can manage this?
So,
capture that in the summary.
I mean, complex is not mainly a difficult disease. We can have a patient that has a lot of problems, and then we can do nothing. So we say we do nothing, and it becomes not a complex case. A complex case is actually a case that needs a deeper discussion during MTB. So does it have to do with the time information? Maybe the scenario. Maybe we can use the scenario because we didn't yet. But if we have a rule-based approach, we can say that patients after surgery, if they are like this and like this and like this, then they are complex. People after chemo and surgery, if they are like this and that. But we didn't explore more.
Okay. In this section 2, you explained very well that the limitation of your role was because of the number of token limitation. And do you plan to explore a long sequence transformer model? Because I think it will solve your problem and maybe improve a lot.
Yes, I actually started. I didn't get that good results, but it was long former. It was done on English. I don't know. Maybe it's a fact. I may should. And sometimes there are even more tokens than the long former. I think it's 4,096 token or something like this. Yeah, sometimes there are more than 4,000 tokens in the first concept summary. But yeah, I've been reading papers that dealt with these problems. So yeah, I will try to do other things. Maybe also use large language models, maybe to summarize the MCP.
I have also the feeling that an important topic related to the use of AI for such medical purpose is concerns the explicability method that can be used to explain the result of, for example, your classification of or similarity measurement. Do you plan to use this type of method? I was thinking to attention, sharp line, things like that.
Not really familiar with this, but yeah, they're definitely hoping to use. I'm not a fan at all of having the system. Actually, even with the complexity part, we prefer the hybrid part because when we get the weights that are provided by the machine learning algorithm, we have weights for each attribute, so we can explain. So the algorithm gives that importance to this attribute, and that's what I like. But for the complexity learning, we don't have that. Actually, we just have concepts, we learn, and it classifies good. But it's definitely, it's definitely a good idea to have explainable AI and explaining the results.
I think it would be very nice to consider them as like as those techniques now exist and you can it's another component you can have in your pipeline, maybe to explain some results. I have also a question about similarity measurement. You only compare static data about a patient, and I imagine that it's possible to have dynamic patient data that evolve over time. And I think in your perspective, in your manuscript, you mentioned a representation of the patient as a graph, the work of I noticed, I don't remember who, but
something like in that work.
do you plan to, how do you plan to use this type?
Yes.
In a PhD as supervised, we try to use this type of representation for prediction task, and the result was not so good, but I think it's very well functioning because it improves the representation. It's easy to represent the time and not to aggregate all the medical events of in a vector. You can have the evolution.
So it's actually what we plan to do. I mean, in fact, when we was doing the similarity, we was the last step. I'm not really familiar with the knowledge graphs, neural networks. So I knew that I had to learn about it then to start using it. So we didn't go with it, but it will be actually easier for us because we have our pipelines that extract the patient in the ontology. In the ontology, you have three main entities and they are related, so it's a kind of graph. So yeah, the next plan is to do this type of techniques to evaluate the similarity.
Okay, I will finish now my question because we have to listen also all your supervisors. So I will start with Jack.
Okay, thank you very much.
Thank you.
Well, I would say that indeed Akram did a lot of work. I will not comment on the scientific part because I'm some part of the work as a co-supervisor. And if you don't mind, I will continue to comment in French for the français. Okay. Donc, je continue en français pour dire, je vais commenter plus sur notre interaction pendant toutes ces années. Alors, j'ai réalisé que ça faisait en fait bientôt 5 ans que tu étais dans le laboratoire, depuis 2019, et ton master en informatique biomédicale. Alors, je me souviens que j'ai été frappé par au début ta motivation, ton envie de bien faire les choses, ta curiosité aussi, et le fait d'essayer tout un tas de choses dès qu'on te donnait une idée. Et ça n'apparaît peut-être pas ici, si vous avez des questions sur est-ce que pour essayer ci et ça. Mais c'est vrai, enfin, tu l'as dit, tu as essayé pas mal de choses sans ménager tes efforts, donc vraiment une capacité de travail importante et c'était très agréable pour ça de travailler avec toi. L'autre chose sur le plan humain, j'ai beaucoup apprécié avec Akram, il est toujours de bonne humeur, il est toujours content, il a toujours le sourire sur le visage et c'est vraiment un plaisir de travailler avec toi. Alors évidemment, tu as fait un travail de recherche. Alors quand on fait un travail de recherche, on a des déceptions, puis il y a des choses, des satisfactions. On apprend des choses. Alors moi, je sais qu'il y a une leçon que tu as apprise sur le tard, là, et que les adultes en général connaissent, c'est que le temps n'est pas extensible. Et voilà. Et alors, juste une petite question comme ça, à titre personnel. Donc là, tu termines 3 ans de thèse. Finalement, quelle est la leçon que tu as apprise de ce travail de recherche? Si tu dois dire que quelque chose t'a marqué.
C'est en rapport avec son commentaire, c'est qu'en recherche, on travaille toujours backwards, on n'est jamais dans les temps. Du coup, je fais passionné par ce domaine, ça m'a juste donné envie de creuser encore plus cette thématique d'aide à la décision et continuer de travailler.
Voilà. Okay. Voilà, donc je termine mon commentaire et je passe la parole.
Thank you. Thank you, Jacques. We will now listen to Joseph Gligore.
Thank you. May I give 2 kinds of comments? One is more general regarding the question you asked. This is the easiest way to take the decision when you take care of breast cancer. We are just dealing with early breast cancer. So we are not dealing with the metastatic one. And the most difficult thing is how to predict what is unpredictable. Because at the end of the day, those patients are operated. And let's say by 50% of them will be probably cured just by surgery. So the main discussion we have is how to add endocrine treatment, chemotherapy regarding different parameters. And back to the work that Brigitte and the teams made since many years, even if it maybe doesn't fit or doesn't look like this, I'm a supporter because, as you mentioned before, time is limited in clinics. And when we have to take decision, usually on Thursday morning, we have 50 cases to discuss in 2 or 3 hours. So the subject that Akram treated is mainly important for us because it could help us to classify the priority that we have to discuss. And try to understand what is a complex case doesn't mean, as Akram mentioned, that the pathology is complex, that the decision-making is complex. And back to, I totally agree that there is a lot of parameters that you might include regarding the psychological things, etc., etc. But at the end of the day, what we have to answer is what is the optimal treatment recommended? Then the second part that is not on here and that missed in a majority of type of, I would say, approaches regarding the help that you might provide with the systems, is the correlation between what we decide, what has been done, and the final issue, which means, do the patient is still here without any relapse? Have we made a mistake? And this is a big part of all the works that we need, because this is helpful. This is the first step, very important. But at the end of the day, when you ask even the greatest thing, is all of data, there is a very, very small amount of information in the real world data that the decision we make is clearly correlated to the improvement of the patient care. And try to just demonstrate that the multidisciplinary team approach might help the patient to be better at the end was a big challenge during the last years. So I think that this approach is very important for us. Medicine is not a science. It's a practice that use science, which is a little bit different. We are not scientists, we are practitioners, and we use science. And the fact that you use science to try to understand how we think and how we make the decision is really important for us. Sometimes it's a really black box for us, and it's complex, and we maybe don't have time to understand. But I enjoyed working with Akram, even if it was very hard for him because he had to just follow me sometimes, try to ask me about several things. It was a nightmare for him. But in any case, first is he was very motivated, and second, he understood several things. I think that one thing is what is written, one thing is how we discuss. And the most complex thing that do not appear here is in a multidisciplinary team decision, the people that are here and I will say the level of the team's expertise might influence also the decision. And this is a big, big challenge for us. If we have a system that helps us just to classify the patient, saying, okay, for this one, clearly we need expertise. For the other one, as you mentioned, probably that using the system, it might help just to be sure that we don't make simple mistakes. It will be a time saver for us and be more helpful for the future. So just 2 remarks, or 3, sorry. Olivier, you mentioned the Taxol story. Just to get you the information that since the beginning of the history of chemotherapy, we now know that for 2/3 of the patients, there is half of them, when we do chemotherapy, it's for nothing. And this is the last, I will say, 5 years when we get this information. So it's normal that when you look at the big database, you will not find a signal that during 4 courses, 6 courses, or 8 courses. On the future, what we know is that probably if we better define the people that really need chemotherapy, then it will probably make a difference having 4, 6, or 8. So this is one of the points, but of course, these kind of tools that you mentioned helps us to understand that what we think for a big population is not exactly extractable for one person. And what we need to do is, let's say, move from a general consideration of what is the guidelines to the people that we have in front of us, which is really complicated. The second point you mentioned, the guidelines. I agree with you, but the granularity of the guidelines might be different. If you want national or international guidelines, you need a very, very small level of granularity because you don't have access to all the type of diagnostic tools, treatment potential. The second thing is that in France, it has changed last year, but or last month even. Since the beginning of the National Cancer Institute, it was mandatory to have for each region and for each organization their own guidelines. The national guidelines were not considered to be enough, and you need to have your own guidelines. It was a little bit complicated because in the majority of the cases we share the same information. But this is one of the points, just to answer your question of that. So now the second step, again, I mentioned it before, it was really a pleasure to work with Akram and Brigitte for this project. I think that it's helpful. It's not the end, it's just the beginning. I don't know if you continue on this way, but I think that it will help us to understand how we think, because sometimes we think fast and it might be okay, but it might be also wrong. And what I will just recommend to Akram, this was a nice presentation, but I'm sure that 99% of the medical doctors will not understand nothing. Give just the simple, I will say, information to us. We are very limited. But congratulations.
Thank you. And now,
Alors, moi, je vais le faire aussi en français, comme ça, d'abord, c'est simple. Et puis, ça permet voilà. Moi aussi, évidemment, j'ai rencontré Akram en même temps que Jacques, donc il y a 5 ans. Alors, c'est vrai qu'au début, en fait, il était étudiant en master et il a appris un sujet de stage qui était un sujet sur Oncodoc. Assez tôt, il est rentré dans la prise en charge, l'aide à la décision pour la prise en charge du cancer du sein. Et puis après, il a continué à travailler dans le laboratoire en attendant d'avoir une bourse pour sa thèse. Et quand il a eu sa bourse sur sa thèse, donc il a pu commencer à travailler sur les sujets qui l'intéressaient. Et on a passé donc ces 3 dernières années en interaction régulière, on va dire, avec donc Jacques et effectivement Joseph. Bon, je crois qu'il a dit ce qu'il fallait sur le plan technique et scientifique. Je ne vais pas rentrer, puis c'est pas mon rôle en même temps. Mais de rejoindre Jacques sur le fait que c'était très agréable, effectivement, de travailler avec Akram, qui est effectivement curieux, motivé, mais souriant, ça c'est clair. Mais alors, je vais aller peut-être un petit peu plus loin et dire que c'est vraiment un vrai chercheur au sens de, il n'y a pas un truc qui va laisser parce qu'il lui résiste. C'est cette obstination, donc ça c'est vraiment agréable, parce que moi je suis un peu pareil. Donc, cette obstination que je trouve est vraiment sympathique et qui permet finalement de détecter des choses qu'on n'aurait pas vues a priori. Donc ça c'est vraiment bien. Et puis, bon, c'est vrai qu'on a la chance finalement d'avoir encore pendant 9 mois. Donc, l'équivalent d'une grossesse, donc c'est pas de quoi on va couper. Mais effectivement, il a bien retenu le fait merci Olivier, le fait d'avoir des publications dans les journaux, parce que c'est vrai que c'est plus facile d'avoir une publication dans des conférences, mais en même temps, ça marque aussi des étapes dans la progression, plutôt que d'avoir quelque chose qui est déjà bien plus abouti ou plus mûri, on va dire. Donc ça, au moins, ça a l'avantage d'être ça. Et puis, voilà, l'évaluation, parce que comme il l'a dit, il y a pas mal de choses qui n'ont pas été évaluées, il y a des choses qui ont été effleurées, et donc qui sont techniquement valables, mais on ne sait pas ce que ça donne en pratique. Et donc ça, j'espère que ça sera des choses qu'on aura le temps de faire, et avec l'aide de Joseph. Oui, parce que quand on a parlé finalement de manque de disponibilité, c'était beaucoup de la sienne.
Il y a toujours un coupable.
Non, mais bon, il y avait quand même un peu de disponibilité et c'était précieux. Merci. Pas de questions, moi.
Okay. If there are no any further comments or questions, I believe it's time for the jury to enter into deliberation. I don't know if we stay here. Okay.
And all the people go